Right.
So Charles, what day is this?
This is Wednesday.
It's March though, right?
It's March 1st.
Yeah, where's the rain?
I don't know. It's in Cambridge, where these gentlemen are from.
It's supposed to rain in Seattle until what, May or June?
Well, hopefully
Anyways,
it's not
where are we?
we're at Lake Bill
And why do they call it Lakeville?
because his office is around here somewhere.
Yeah, it used to be, I think. This is one of the first. These are the first buildings that Microsoft built. So this is the original campus. So it's sort of fun.
Yeah.
And who are the gentlemen with you?
Well, we have a couple researchers from Cambridge, England, who are visiting Redmond for Tech Fest. We have Karthik and Andy. And what are you guys doing at Tech Fest? Why did you come all the way over here?
Right here,
what are you
the
showing?
lights, sort of. Let's go over here.
So we've had a research project for a few years on web services security, and we've done a variety of things like security reviews, and we've built formal models that we've analysed with theorem provers. But the thing we're coming specifically to show at TechFest this year is a new tool that's available as a download that plugs into the Microsoft Wizzy product, and it looks at the configuration files that set the security policies for Wizzy.
And let's talk about what Wizzy is.
Yeah. So Wizzy is a toolkit that implements the new WS star specs. It implements WS security, which is like a syntax for adding signatures and encryption to SOAP messages, and that's the core of it. But there's a bunch of other protocols it implements, like WS Trust and WS Secure Conversation.
Yeah.
And the thing is that ASP.NET itself doesn't implement. It implements SOAP messaging.
Sure.
But it doesn't do this new security stuff. So Wizzy is an add-on that implements those features and lets you secure your messages to a web service.
That's fantastic. So we can. And how long has this been around?
Wizzy itself has been around for around 3 years now.
Okay.
And the version 1 came out around 3 years ago.
Okay.
And version 2 came out about a year ago. They just released SP3 of version 2. So there's a lot of people who are using this toolkit already to write their web services.
Sure.
We're concerned about how secure those web services are going to be.
Because that has always actually been a concern of people, like the security and like how do I lock down my web service? How do I make it secure? And so that's something that's relatively new.
Yes, considering that these web services are going to be available over the public web pretty much to anybody who wants to use them. And they're going to be using HTTP, which means they can punch through firewalls as well. People have been very concerned about what people can do using these, bad guys can do using these web services.
Absolutely.
How to break into systems. And but we've been concerned about how we can stop them, or more likely how we can statically analyze these protocols and the implementations and the policies people are using, for instance, which is what we're demoing today.
Sure.
On how to kind of make these secure so that nobody can break in.
Fantastic.
Yeah.
Fantastic. And as you mentioned, it's implemented as a plugin in Visual Studio. You mentioned something that kind of caught my ear, a theorem prover. Let's talk about that for a second, if you don't mind. Like,
Okay.
What is a theorem prover?
What's a theorem prover?
Yeah.
Well,
Sounds interesting.
So if you so you have to have a specification to begin with. Supposing there's a bit of software you want to build or you've built, and you want to get strong confidence that it's actually doing the correct thing. Like in the Wizzy case, it would be that it's ensuring the secrecy of messages, or it might be that it's ensuring the authentication of messages, so that when you receive a message, you know who it came from, or correlation, where if you get a reply back from a service that you send a request to, the reply is actually, the service thinks that's the reply, or that's the reply that the service generated for that particular request. Okay, so these are all kind of properties you might want to establish.
Sure.
So a formal approach to web services security is to write down a formal specification and a formal logic of the properties I've just described. And you can do that by and then having a formal model of the behavior of the service, and then showing that the formal model actually meets the specification. And that's where the theorem prover comes in. It proves a theorem, which is that the specification holds of this model.
Fantastic. So that's really what your tool is doing then, in a sense, right? I mean, you're proving that you're statically analyzing somebody's implementation and saying, well, based on what you think it's going to do, it's actually not going to do that for these reasons.
Right. That's almost right. So we've done two
That's
tools.
the story of my life. Sorry.
So we've done a couple of tools, right? The sort of trajectory of the project has been, we first of all worked with the Wizzy guys and took part in security reviews and helped, you know, find various bugs before the product went to market. And then we built this formal language that we call toolkit, which is a version of the Pi calculus. That's so it's a formalism for concurrency that's been around for about 15 years. We built a tool that would allow you to write these toolkit descriptions and then have these specs that I described, and then the theorem prover would actually prove that the toolkit descriptions of the protocol were actually correct. But what it wasn't doing was showing that the actual implementation was correct. There's always a gap between the toolkit code that's in its idealized language and the actual implementation code. So, you know, so it's really worth doing that for a formal model of the protocols that are built into Wizzy, but it doesn't really help so much with the particular protocols that a user might customize Wizzy to perform.
So basically, we have the second tool which we're demoing today for that reason, which is the Wizzy Policy Advisor, and this is so we've already released the toolkit language and tool, which is the theorem prover, as you might call it. It's been out there for quite a few months, maybe 6 months already. And the other tool, which you just released around 10 days ago, and a new version came out yesterday, in fact, is the Wizzy Policy Advisor, which is what we're demoing this year. The toolkit we already demoed last year at TechFest.
Interesting.
So
Sorry we missed that one. Of course, we weren't around last year at TechFest. Yes, we were. Almost we were. We haven't been around that long. But that language sounds incredibly interesting, and I'd love to talk about that a little bit at some point.
Okay.
Sorry to interrupt you.
no, that's fine. It's just that the toolkit language and the prover are really meant for researchers or experts who are also interested in web services security. We've kind of geared it towards that kind of demographic. Whereas the policy advisor is meant for developers, everyday developers, writing their web services, writing their own policies in Visual Studio.
Sure.
So that's the kind of the two level of tools that we have out there right now, and both from the same group in Cambridge. We call ourselves the Samoa group. And,
The Samoa group.
The Samoa group.
Interesting.
Yeah.
So now, if you're a developer who is, I guess, very competent. I don't know when you say you created something for a researcher versus something for a developer. Does that language enable a developer to extend the tool in any way? So, in other words, let's actually just talk about that. Is this tool extendable?
So which tool?
Sorry, the one that you're demoing today.
Oh, okay.
It's no. No. It's no. It has a fixed collection of queries. It looks at about 35 specific things that might be wrong with a policy.
The geeks wanted to have their word in the video too. Why don't we go over and see a demo actually?
Okay.
Yeah.
Okay.
Now on the way over, if I may ask, what language is it written in? Tool.
The policy advisor in C#.
Okay.
And toolkit is in a mixture of languages. Oh no, it's mainly ML.
It's OCaml or F#.net. In fact,
F#.
Yeah, F#.
Wow.
Interesting. It's a Microsoft functional language, which is a version of the OCaml language which was developed originally in France.
How does that language differ from others you've worked with?
And did you want to take the functional language spiel later?
So it's not object oriented. It's a procedural language. So it's strongly typed, but objects aren't part of the type system, and you have function types, primitive or procedure types. So I guess we've been sort of waging a guerrilla war to get ML into Microsoft. Ever since the Cambridge Lab started.
Sure.
So we've been using ML for lots of different projects. Like we had so Don Syme is the guy who did who did F#, the language you use to do toolkit.
There's a boot you can go to learn more about F# if you wanted to.
Sure.
Which you believe will be the next cool language that everybody should be using for certain purposes.
For certain purposes. those purposes being
Writing theorem provers, for instance.
writing theorem provers.
So that's not the only purpose.
But now,
but ML is.
I want to prove. I don't think F# will work though. That's cool. Very interesting. So let's demo. Let's. Are we going to be able to demo in this
Yeah,
light,
we
Mr.
should.
Scoble?
Okay.
So.
So
It might be a little bit glary. If you can bend the screen a little bit toward you.
I'll see if I make it brighter.
I'm seeing it, so that's fine.
Okay, so let me start with Tulafali,
Sure.
and then I can move to Policy Advisor, and then that gives a.
Be nice to see what that
that'll,
language
that'll
looks like.
give you a kind of a feel for the difference between a researcher tool and something we think customers would make good use of. So let me. Where are we?
Research tool looks like.
Yeah. So let's pop this open. Okay.
Zero UI.
Zero UI. So we've opened up the code in Emacs.
All right.
So actually, Karthik, do you want to?
No,
Sure,
no,
that's
let
what-
me just go on.
Oh, okay. Okay. So
That's how one person handling
okay, so the story in this situation is that we're considering a request response protocol where there's going to be multiple services, and they're going to authenticate themselves using an X509 certificate, and then there's multiple users, and they're going to authenticate themselves using a password that they share with the service, and we build a formal model in this PyCalculus, which you can see down here.
Can we get that?
Where's it?
See this bit here? That's the whole system.
And that's
in,
PyCalculus?
That's PyCalculus. Yeah. So it's a very simple language based on just the exchange of messages, and in our case, we also can evaluate predicates in a logic programming style.
Okay.
So we've got a little bit of code there that represents multiple clients, and a bit of code that represents multiple services, and then they exchange messages. And I can show you the code that generates the messages. So up here, we have this logic predicate envelope 1 that gives you a description of the SOAP message that's being sent. So we use we have a sort of literal syntax for XML built into the programming language. So you don't have to use a DOM or something to describe XML. You can just write it down. So you see here, you've got. Oh, I can use the mouse. So you've got the envelope there with a header and a body, and the header's got it's got a couple of addressing headers, 2 in action, and then it's got some headers that can be used for replay detection, the message ID and a timestamp, and then it's got an encrypted username token that is going to identify the client, and then a signature which is going to authenticate that the message comes from the client. So then we have got code for the client here. I'm not going to go into the details of it, but we've got a process here that is acting as a client, and it's making message 1 here. I can use my mouse. Makes message 1 there by calling this predicate make message 1 that puts all this data into the message, and then it outputs it on the SOAP channel, and then it waits for the reply message 2. It checks the signature on it, which is done by calling another predicate, and then it finishes. And the stuff in red here this is where the specification comes in that I was speaking about earlier.
Okay.
That we want to show that a message 1 is authenticated. So the way we do that is we have a begin event at the start that is like the client logging that it's trying to send a message with particular data. Then after it's received by the service ends an event with the same data. And the idea is that you always want it to be the case that whenever the system is interacting with the environment, that every time there's an end event with particular data, there's a preceding begin event. So they've reached agreement. So if there's an attack, so the kind of attacks we're worried about is where someone takes a message that's say sent to Alice, and say if the 2 part of the message wasn't signed, then an attacker could sort of scrub out Alice, put someone else's name on it, and send it to the other guy, Bob, say, and then Bob will think that it's been sent to him because he's got a valid signature on the message. So the trick is that the the attacker hasn't actually broken any crypto, doesn't know any passwords, but has been able to replay the message to another person. And this spec would be violated if that happened, because the end event would disagree with the begin event. So then, to show the theorem prover, so this is particularly an impressive part, I'm afraid. It's not much UI. So we run tf on this laden.tf file, and it runs away.
This is a very simple example. Sometimes we take all night long to run the theorem prover as well. So it does a lot of analysis. What it's trying to check is for all possible attackers in the world who do a lot of things, whether or not this particular protocol is simple. So the protocol itself could be as simple as you saw, just a page or two of code, but you can't really tell what the attacker can do. He can swap messages, redirect messages, change parts of the message into something else, use two messages and combine them into one. There's effectively an infinite set of things that you can do, and you have to actually be able to prove that the protocol is secure despite this infinitary behavior of the attacker. So, and this too in the presence of multiple sessions between the client and the server. So you can't really say this protocol works if there are 2 clients and 2 servers in the world. It has to work for as many servers as there can be, and as many sessions between as many clients and servers as there can be. And that's all that has been proved. All of that has been proved in the last, 4 seconds for this protocol. So it's a fairly heavyweight analysis, and for more complicated protocols it takes longer, of course.
Except it hasn't in this case, because it's actually it cannot be proved. So this is kind of demo.
Cannot be proved.
This is demo disaster, but it's because I was demoing yesterday, and actually we'd seeded a bug. So what it's saying here is that the C1 agreement on message 1 can't be agreed. So it's actually discovered an attack. And that's because we had commented out a bit of the script that represents the signatures. So if can I show you that? Just so we'd had it not include the message ID in the. So we've not signed part of the message. So then the attack is that the attacker can change the message ID and cause a screw up. So if I.
And you won't be able to verify that it's the original message.
In fact, it automatically generates a counterexample trace, which you can use to construct an attack on a real server if you want.
Fantastic.
It's just a little unreadable for, which is why we say this is for experts right now, because the trace is quite complicated to read, but it's an HTML trace which you can read through and get the messages and actually use that to mount real attacks if you were so inclined.
Fantastic.
But all is well. Run it again, and this time it's been able to show that by adding the signature, we've been able to prove agreement on both the first message and also the second message, and correlation between message 1 and message 2. And this part down here, this is just showing that both C1 and C2 are reachable. Because it's very easy when you're doing formal modeling like this to get a system that doesn't actually do anything, and then it's sort of vacuously secure because it doesn't do anything. So we need to check that it actually can run to completion. So
and it's safe.
And credit, we should give credit that we. So this is a tool we built in MSR Cambridge, and we've made use of this ML language, and also we made use of this tool called proprietary, which is done by Bruno Blanchet in Paris. So you can see the situation.
Effort here. Huh?
Absolutely.
Cambridge, Redmond, and Paris come together.
Do you guys get to take expense-paid trips to Paris to go work together?
No comment.
No comment.
Well, that's interesting. It's very interesting.
So this code was partially written on the Champs-Élysées,
Champs-Élysées.
I can't even say it.
So this is
this influenced by good red wine, or?
No.
Steady on. Yeah.
I'm just kidding.
So clearly, this is the you need to have a PhD and really understand what's going on. But for the average developer like me, how do I use this stuff in Visual Studio?
Okay, so that's our second tool. So let me show you that. So now I've got here one of the. I'm in Visual Studio, and I'm looking at the policy in one of the samples that comes with E2. So this is an XML security policy that governs the signatures and encryption on one of the samples. It's actually a very simple sample. It's simpler than what I just talked about. So we've got a request and response here, but only the request is secured, and it's secured with a signature derived from a username. But there's no
So you know that the request is coming from a certain individual.
Exactly.
But the response is it doesn't matter. Okay.
Right.
It's a sample which comes with Busy 2.0, and in this case, they were just illustrating how to do security rather than.
Fantastic.
Yeah.
So this XML is it's kind of low level, and it can be hard to get it right. And we discovered in security reviews various kind of common sort of failure modes. So we built a tool that can search for them. So let me just let me show you that. If I move over here,
Where's your mouse?
I'm over here.
Yeah. Okay.
So if I right click, so I go to the WYSI settings tool. Okay, and so this is a tool that lets you set various parameters of WYSI 2, including policies. I move to the policy pane. And what we've got is that WYSI have a hook that calls our tool that they put into the product. So if I click on the advise button, it pops up. So this is now the policy advisor. And what we've got is a view of the policies for this this sample. So let me click on say that policy. So this is showing that the policy that signs the message, and we have a summary up here of what that XML has actually done. So we've got a table that just interprets what the XML does, just to give some sort of understanding. So it's listing all the headers that we've been speaking about, like the to and the action, the message ID, and so forth. And in this case, they're all signed, provided they're present, and the ones that really matter are also mandatory, and the body is also signed. So that's great. But down here, you see the some warnings that have come up on this policy. Now, we have to some extent guess what the tool has to guess what the protocol is, so it can't be completely sure what the goals are. So it's called out that there's no policy for responses, and it's called out that there's no policy for, rather the policy for the request doesn't call for confidentiality, and that may or may not be a problem. So we can't tell. So we tell the developer, and they have to decide. You have to sign the security review. But there's one issue that is a problem, which is that we're using an unencrypted username token in this sample for signing messages. And if we look up to this part of the pane, we get a description of what the problem is, which basically is that the username token has been used to derive a cryptographic key from the password. And then it's been used to sign the message. But there's not enough entropy to secure that signature. So if the password is just a weak, user memorable password, it would be possible for someone to do a dictionary attack on that signature. So that's why, say, in the sample I showed earlier, we were encrypting the username token. And this is like standard practice. There's now an MSDN article that's just come out that explains how to do this. But people won't necessarily do that. It's great having an MSDN article, but it's even better to have a tool that can search for these kind of issues.
Absolutely.
So that's what it's doing there.
So this is a sample of 3 issues that you can pull out here, but in general we have 36 so-called patterns or queries that we run on these policy and configuration files to find these errors. And most of these are bugs that we have found in commonly available policy files and policy configurations. So
now when you find a new bug, how do you add that to the matrix, to your tables of understanding? In other words, you have to pre-understand things, right?
Right.
So if I find a bug, or if someone finds a bug, and it's a good attack, something that probably you didn't think about or whatever, how do we inject that into the tool? Do you have a config file that has all of the?
So at the moment we don't.
Okay.
And effectively what we have is, this is a prototype that we've put out.
Sure.
It's on the research download site. It's unsupported.
Okay.
And we're putting it out in the hope it's going to be useful. And we have a feedback, mailing list that
Fantastic.
people can send comments to. And we're hoping to refresh the bits. Because we're sort of decoupled from the WYSI product, so we can refresh the bits. When when we sort of hit new, decide there's new queries,
Sure.
as you
You
suggest.
just auto-update itself.
Yeah.
And that would be kind of like a virus, like an antivirus software.
Right now, we have not thought about that, but yeah, that would be a end goal of this if this were to become, this were to have legs, as it were.
Well, it's great. I mean, to me, it seems like it should be a natural step in the process of automating security policy development.
Right.
Yes.
It should always be just like when you compile your code.
Right.
In this case, it's sort of you're compiling your security concepts, and the compiler, in this case, would say, nope, that's a bug. Check this out. You shouldn't do that. Or it's beautiful. It's wonderful. I mean, automation is great.
Yeah.
I know I appreciate it because security policy is difficult.
Yeah. Yeah. So I mean, there's the FXCOP tool, that's part of WHDB.
Yes.
And it works for code, for C#
Exactly.
or whatever. And there's no real equivalent for XML.
Yeah.
I mean, in general, we think that's a good thing to do. More and more security decisions now are governed by XML configuration and policy files.
Sure.
So this is an example of the kind of thing you can do, sort of to go look for particular potential threats and misconfigurations in the XML.
Absolutely. Well, that's grand.
The reason we're putting out this kind of tool is that it's all these queries and the bugs that we're pointing out here are well grounded in our formal research, and so these are all found from using our theorem prover, for instance, first, many of them at least, and then we would code them up as simple things to check on a developer's configuration. But most of this actually comes out of fairly formal and.
So what is
technical
this
research.
family? The formal research that you guys do. You mentioned formal research. That's interesting.
Well, in the sense of the Tulafale tool that we just saw.
Yeah.
So we would write formal models of protocols and of what the implementation does.
Sure.
And try to check whether some ways of using that are secure or not. And whenever we find a way of using it which is insecure, we can make a pattern out of that and use it in this tool.
Fantastic. Very cool. It's like super high level white hat. Is it white hat? The good guys? Yeah. Okay.
We're the good guys, all right.
Yeah, the architects. White hats.
Sorry
Cool.
if you get tempted, but
Very excellent stuff. Thank you.
great.